and welcome to Algebra II with Mr. Clausen. Today I want to talk about some real-world applications of exponential and logarithmic models. Some of these we've seen a little bit before, but taking an opportunity now to expand on some additional examples, maybe a little bit more technical than some of the stuff we've looked at in the past. So for this lesson, I want to just crash through 3 examples. I want to look at a sound wave example, an archaeology example, and a population example. And so with that said, I'm going to get started here. And one of the things that we want to be able to do is, now that we have some basic understanding of logarithmic and exponential functions, we can go and we can answer some questions like this one I have here. And the sound example I have is that the human threshold for pain is 120 decibels. Instant perforation of the eardrum occurs at 160 decibels. Find the intensity of each sound. Okay, and so remember that when we talk about decibels, decibels fit into a logarithmic model. So the loudness, or decibels of something, dB, is equal to 10 times the log of the actual intensity being observed divided by intensity naught. And I naught here is just the baseline. Okay, so if you want to think about a sound that is so quiet that it just occurs everywhere, this is really what this is. And this number is equivalent to 10 to the negative 12 watts per meter squared. And a quiet room, like with no ambient noise whatsoever, still exhibits a certain amount of waves per meter squared that occur. You can't be in a room where there is no seismic activity of any way, shape, or form. And this is considered the minimum baseline that's there. All right, 10 to the negative 12. So if you want to figure out how intense something is in waves per meter squared, all we need to do is we need to plug in the value that we have, plug in the constant I naught, and solve for I. So if you want to find the loudness, or intensity I should say, at 120 decibels, all that we need to do is set this equal to 10 times the log of I over 10 to the negative 12 watts per meter squared. And the first thing I think I'm going to do here is I'm going to use the quotient property of equality. So I'm going to just put this in parentheses because I can do that. And I'm going to set this equal to 10 to the log of I minus the log of 10 to the negative 12 watts per meter second. And so what this would allow me to do is that if I'm looking at this and I want to solve this, I mean, we would just distribute the 10 back across on both sides, or not to do that and actually just divide both sides by 10. We could divide this all the way across. And then what we would get is simply 12 is equal to the log of I minus log times 10 to the negative 12. And one thing I'm going to point out here is that I can use the power property and I can pull this out. And then I could say 12 is equal to log of I plus 12 times log base 10 of 10. And we know that this is equal to 1 because 10 goes into 10 one time. And so what we're going to get here is 12 is equal to the log of I plus 12. And if we take both sides and we subtract 12 from both sides, we see that the log of I is equal to 0. All right, and if we want I all by itself, remember we have to take the inverse of log, so we'll go 10 to the power of log base 10 and 10 to the power of 0. These will cancel. 10 to the power of 0 is 1. So I, in this given situation, or we'll say I, at 120 decibels is equal to 1 watt per meter squared. And so with that, hopefully you can see how some of these operations work and how we can apply properties of logarithms in order to solve this. So with a clean slate here, we know what the intensity at 120 decibels is. Let's find what the intensity is at 160 decibels. And if we want to find the intensity at this given level of noise or loudness, we're going to do the same thing. So I'm going to go through this a little bit more quickly this time, now that I know you've seen it a couple times. So the intensity at 160 decibels by 10 to the negative 12. All right, and I'm going to take advantage. I'm going to use the quotient property. I think that's just the easiest way to do this. So 10 to the log of I at 160 decibels minus the log of 10 to the negative 12th power. All right, close that off. If we go and just divide both sides by 10, I'll see that 16 is equal to log of the intensity at 160 decibels. And let's just use the power property now, pull this out, plus 12, just like last time. And now really the main difference here is now if I subtract 12 from both sides, is I'm going to have 4 equal to log intensity 160. And now if I want to get rid of the log, remember this is log base 10, so if I take 10 to the power of log base 10, those cancel, but whatever I do to one side I have to do to the other. So what I'm going to see here is that the intensity at 160 decibels is equal to 10 to the 4th watts per meter squared. And so if you ever wanted to kind of relate, and part of the reason that decibels systems are, or a logarithmic function is really applicable to a decibel type system here, is that if we want to analyze seismic activity and we want to be able to relate something from the range of 120 to 160, we can actually compare how much more intense the noise is that will perforate an eardrum as the noise that'll cause pain. And what I'll see is that if I want to compare the intensity at 160 decibels over the ratio of 120 decibels, I will see that 10 to the 4th power divided by 1 is equal to 10,000. So what this says is that the intensity at 160 decibels is 10,000 times more intense than 120 decibels. And can be a really useful way to look at a huge range of intensities with a relatively small range of numbers. So let's look at a second example. We've talked about half-life isotopes before, so now I want to look at a carbon dating example. So we have a scientist that carbon dates a piece of fossilized tree trunk that is thought to be over 5,000 years old. The scientist determines that the sample contains 65% of the original amount of carbon-14. The half-life of carbon-14 is 5,730 years. Is the reputed age of the tree correct? Explain. So what they're trying to ask you to do in this given situation, and it's something to take into consideration whenever you're doing carbon dating of anything, is that generally, like when you look at a tree, you know about how much carbon is in it to start with, especially carbon-14, because what happens is carbon-14 decays into carbon-12, and as time progresses, they break apart into other things. And so what they're saying here is that based on a new sample, and they're comparing it to this fossilized sample, 65% of the original sample is remaining. And what you would know is that after 5,730 years, it would be half. Okay, so at 5,000 years, does this make sense? And the argument that they're going to probably strike here is that no, it's not going to be quite 5,000 years as far as the estimate goes, because if you remember the half-life equation, you had your quantity, let's say y is equal to the original amount a times a half-life of 1/2, or I should say the rate of decay 1/2, times the x number of years divided by the half-life. And so one of the arguments that could easily be made here is that we don't know what a is. And actually, we don't really need to know, because if we go and we plug in 5,000 years for x, what we would be able to do is be able to estimate, hey, how many years would it actually take for only 65% of the sample to remain? Okay, so if we said 0.65, we did a percentage of a, and we set this equal to 1/2 x to the 5,730. How many years would it take to only have 65% of the sample remaining? If this equaled 1, that would be 100% of the sample. Okay, and probably the easiest way to go about analyzing this and figuring out the answer is either plugging it into Desmos, or one of the skills that they want to try to elaborate here onto you is that if you say something like log of 0.65 equal to the log of 1/2 to the x over 5730, one of the really useful things that you can do is you can use the power property and pull this out and say x over 5730 is equal to log of 1/2 is equal to log of 0.65. And then if you divide both sides by log of 1/2, or 0.5, those would cancel. Let's just bring it over here. And then we could say x all over 5730 is equal to log of 0.65 divided by log of 1/2, or 0.5. And so if we go and multiply both sides by 5,730, I'm just going to multiply both sides by the half-life, just get this all equal to x, 5,730. What I'll get then is that x, which is the number of years that it will be estimated to be, is equal to log of 0.65, log of 0.5, times the half-life, 5,730 years. And if we do all this work, what we'll find is that if we take the ratio of these two logs, the number of years is actually only going to come out to approximately 3,561 years. And so if we're looking at a particular sample like this, it is actually not reasonable to assume that the reputed age of this tree is correct. It's actually a significant underscore of the total amount of carbon-14 that's there, because based on that amount of carbon-14, that tree is probably only 3,561 years of age, assuming that the half-life is consistent in those type of things. All right, and so this is just a different way of looking at it. All right, so as long as you understand the basic half-life format, and you can get it to this point, and you want to go and you want to solve it in Desmos, I personally don't have any problem with that, or any graphing calculator for that matter. But it's good to know how you can manipulate some of these variables, look for specific values in the power format, and that type of thing. So with that, I'm going to move on to the third example. And I want to talk about a real-world population example. So one of the things that we can do is that we can look at growth factors for states like Florida and New York. And so what I have here is some data from the year 2000 ranking the size of the most populated states in the United States. So New York was the third largest state in terms of population in 2000, and Florida was the fourth largest population in 2000. And so we have these relative populations, and then we have the average annual percentage increase since 1990. And so based on one of the very first lessons that we talked about in this unit, we can actually write exponential models describing the rate of this growth. So again, remember that you have y equals a times b to the x power, and your growth factor here is just b equals 1 plus r. All right, so if you want to have a growth factor for Florida, let's say y of Florida, this would just be equal to the original population of 15,982,378 times the rate of growth, which is 2.13%. So in decimal form, this would equal 0.0213. Okay, which is what I'm going to plug into there. So this will be 1.0213 of x years. And then the y of New York is going to be 18,976,457. And this will have a growth factor of 1.0054 to the x number of years. And again, the 1 is just representing the value of holding the original population, and then the decimal part after represents the percentage growth after each year. And so if you forgot about that a little bit, just remember that, and that's a thing that you have in your toolbox. Remember that A is usually your initial amount or population, and Y is the amount after X amount of time. And so one of the things that we want to be able to do in some of these circumstances is if we are asked when Florida's population might exceed New York's population. And we know that this will happen because the rate of growth for Florida is higher than that of New York, and Florida has a lower population than New York. So at some point they will cross. So what I want to do, if I want to estimate the population of Florida and when it might exceed New York's population, how I'm going to take advantage of this is just say, hey, when the population of Florida is equal to the population of New York, that's when Florida is going to overtake New York. I can see Florida has a larger rate of growth than New York and can reasonably explain this. Now, I'm going to tell you not to go and plug all this in, use the logs, split it all apart. I tried it. It was a little cumbersome. And the reason I just tried is sometimes when the examples are a little bit smaller, it's honestly just faster to just apply the log relationships and just go for it and try it. But in this given situation, what I'm going to do is I'm actually going to just graph this out on paper here and then show kind of what it looks like here so that you can gain a little bit of an understanding. And so what I'm just going to do here is if I graph this in Desmos, what you should see, or any graphing calculator, is, we're going to see this type of graph where you have one population that goes, and if you have a slower rate of growth, I'm going to over-exaggerate this a little bit. You'll have something like this where it'll cross at, let's say this is New York, and it crosses at, when years are equal to 0, we're at 18 million. And Florida might be here as well, and they're going to have a faster rate of growth, but they're going to start at a little bit lower number. And then what you'll see, and this is over dramatized, when you see this in Desmos, you'll be like, oh, the lines are like on top of each other. But what you'll notice is that as Florida has a higher rate of growth, eventually there will come this point where they will intersect, And when they intersect in this particular example, I would encourage you to plug it in Desmos and give it a try as you're going through and trying to see how this all works out. But what you should notice is that they will intersect at about 2011, so in 11 years after the point where that is. So when x equals 11, these two functions will intersect. So with that said, I hope you got a lot of useful tools out of this video and that you got a refresher on some examples that you've seen before. And with that said, let's do some math.